So we're going to start this deep dive with what sounds like a question that should have been settled centuries ago.
Right.
How do we definitively know that our moon is actually a moon, a satellite of Earth, and not, just part of a binary planet system?
It sounds like such a simple, almost academic question,
Mm.
but it's really not, especially when you look at the cosmic scale. If you ask someone, they'd probably just say, well, the moon is tiny compared to Earth.
But that's all relative, isn't it? I mean, most moons in our solar system are thousands of times lighter than the planet they orbit.
Thousands. Jupiter's biggest moons, for example, are just completely dwarfed by the gas giant.
But our moon is, well, it's kind of an outlier. It's only about 80 times lighter than Earth.
Yeah.
And when you put that ratio next to others, our system suddenly looks a little less like a typical planet-moon pair and maybe a bit more like a close binary.
And that ambiguity just skyrockets when we start looking elsewhere. I mean, take the classic example, Pluto and its companion, Charon.
Yep.
They are so close in mass. Pluto is only about 8 times heavier than Charon that they absolutely function as a binary pair.
Or what about some of these massive exoplanets we're finding?
Oh, exactly. Like TOI 2379b. This thing is 5 times heavier than Jupiter, but it's orbiting a star that's actually smaller and lighter than our sun.
Wow. So with those huge variations, how do you even begin to draw a single universal line between a moon and a binary companion?
Well, that is our mission for today. We're going to cut through all of that ambiguity. The sources you found for us point to a concept that provides a much superior, physically meaningful way to classify these things.
And that's what the sources are calling the Trojan test, or for the orbital mechanics folks out there, the L4-L5 instability threshold.
That's the one. It offers a really clear, elegant answer that just ignores all the confusing stuff like distance and density.
Okay, but to really appreciate why this new test is so good, I think we first need to understand what's so wrong with the old one.
Absolutely. We need to unpack the fundamental failures of the method we've all been relying on for decades.
Right, and that's the one we were all taught in school, the barycenter test. The rule was pretty simple. For the smaller body to be a moon, the barycenter.
The common center of mass.
Right, the common center of mass around which both objects orbit. It has to be located inside the larger object.
And if it's outside both of them, it's a binary system.
Simple.
It seems like a beautifully tidy definition on paper. But let's really get into this, because once you start introducing real physics, it just completely falls apart.
Okay, so let's start with problem number 1. The barycenter rule doesn't really test the physics of how things move. It's more about geometry, and that geometry is easily distorted. So what throws it out of whack?
The main culprits are density and distance. The barycenter's location, it's determined by the mass and the separation of the two objects.
Okay.
But the actual size of the objects, which is all about their density, is totally irrelevant to the physics, but it's everything to the barycenter test.
That sounds like a recipe for some cosmic misclassification. Can you give us an example of how that density problem plays out?
Sure. Imagine 2 bodies, let's call them object A and object B, and they have the exact same mass.
Okay, identical mass. A perfect binary system.
By every measure of gravity, yes, a textbook binary. They orbit a point exactly halfway between them. But now, let's say object B is incredibly large but has a really low density. Maybe it's a huge gas cloud or a super puffy planet.
So it's big, but it's not dense.
Precisely. It's really voluminous. So because the center of mass is halfway between their centers and object B is just so huge, that center of mass could easily fall inside object B's radius.
Ah, I see.
And just like that, the barycenter test forces us to label that quintessential binary system where the masses are equal as a satellite orbiting a planet.
So the classification changed just because one of them was puffy. That has nothing to do with the actual orbital dynamics.
Nothing at all. It's a huge flaw for any kind of universal standard. And it works just as badly at the other extreme when you bring in distance.
Okay.
So consider a planet orbiting a star that's 1,000,000 times more massive.
Right. Nobody would call that a binary system. It's a star and a planet.
You'd think so. Yet if that planet orbits far enough away, say 10 million times the star's radius, that sheer distance can actually pull the barycenter outside the star's boundary.
No way.
Yes. And the math then demands that the barycenter test incorrectly labels it a binary system, even though the mass ratio is 1,000,000 to 1. It shows the test is just way too sensitive to distance.
What a nightmare for anyone trying to classify a new system. And I'm guessing this gets even worse when the orbits aren't perfect circles.
Oh, absolutely. Real orbits are almost always elliptical. So the distance between the two objects is constantly changing. As they get closer, the barycenter moves in. As they swing farther out, it moves away.
Which means the system's classification is constantly changing.
Exactly. For a sufficiently elliptical orbit, the center of mass would repeatedly move from inside the larger object to outside it. You'd have a system that literally flips from being a planet satellite to a binary pair and back again, maybe every single orbit.
That's a bureaucratic threshold. It's not a physical classification.
And that gets to the deeper conceptual problem here. The movement of that center of mass across a planet's surface is, as the source calls it, an intellectual threshold, not a physical one with physical consequences.
Right. There's no physical event that happens.
None. What actually happens when the barycenter crosses the surface of the sun? Nothing. The orbital mechanics don't change, the objects don't suddenly start behaving differently.
Which is so different from other definitions we use in astrophysics.
Yeah.
Those are all about physical cutoffs.
Think about what it takes to be a star. There's a specific mass threshold for fusion to begin. Below it, you're a brown dwarf. That is a hard physical line. Fusion either happens or it doesn't.
Or orbital escape.
Or orbital escape. If the eccentricity hits 1, the trajectory changes from a closed ellipse to an open escaping hyperbola. That boundary of 1.0 has real, immediate physical consequences.
So we need a classification method that's anchored in a hard, observable physical consequence, just like those.
And that search leads us directly to the stability of something called Lagrange points.
These are some of those fascinating features of orbital mechanics. You're saying they exist in any two-body system.
Any two-body system, a star and a planet, 2 planets, you name it, you'll always find 5 special spots known as L1 through L5.
And at these points, what's happening?
At these 5 Lagrange points, the combined gravity from the 2 big objects perfectly balances out the centrifugal force from the system's rotation.
So if you put a small third object there, like a spacecraft,
an asteroid, a cloud of dust, it will just orbit in perfect sync with the 2 massive bodies.
And we use these all the time. The James Webb Space Telescope is parked at the Sun-Earth L2 point, for instance.
That's right. But the key here for the Trojan test is the stability of those 5 points. L1, L2, and L3, the ones on the line connecting the 2 bodies, are fundamentally unstable.
So you drift away.
You'd slowly drift away unless you use thrusters for constant correction. They're useful, but you can't just park something there forever.
But L4 and L5 are different. They're the ones that form perfect equilateral triangles with the 2 main bodies. And they're famous for being stable.
They're like the parking garages of the solar system. You put an object in L4 or L5, and it just stays there, orbiting ahead of or behind the smaller object. This is where we find Jupiter's Trojan asteroids.
So this stability is the core mechanism of the Trojan test. Why are L4 and L5 stable when the others aren't?
It's mostly due to the Coriolis effect acting as a kind of a restoring force. If a little object at L4 or L5 starts to drift, the system's rotation causes the Coriolis force to kick in, and it gently pushes the object back toward the stable point.
Like a marble rolling in a shallow bowl, it always comes back to the center.
Exactly. The physics of the 3-body interaction creates a little gravitational well where the object is safely trapped. No fuel needed.
Okay, so we have these stable parking spots. But here's the kicker, the piece of information that turns this from just an interesting idea into a definitive classification tool. These L4 and L5 points are not always stable.
And this is where it gets really powerful. The stability of L4 and L5 is conditional. It only works if the primary orbiting object is more than 25 times the mass of the secondary object. That 25-to-1 mass ratio is the hard physical cutoff we've been looking for.
So that's the line in the sand. If the larger object is, say, only 20 times the mass of the smaller one, those L4 and L5 points become unstable.
That's the definition. If the 2 objects are too close in mass, too much like a binary, then that restoring force from the Coriolis effect just isn't strong enough anymore. L4 and L5 become unstable, just like L1, L2, and L3.
And you can't park a natural asteroid in an unstable point.
You can't. So the system can't host natural Trojans, and that gives us our clean, physics-based definition.
The Trojan test. You can only have stable, permanent Trojan asteroids if the central object is at least 25 times more massive than the object orbiting it. If it fails that test, it's a binary system.
And it's a purely mass-based classification. It's totally independent of density or distance, which solves all the problems of the old test.
Okay, let's apply this. We can finally go back to those fuzzy examples and see how it works.
Let's do it. Start with the classic ambiguous pair, Pluto and Charon.
Right. Pluto is only about 8 times more massive than Charon.
which is far, far less than that 25-to-1 threshold. So the L4 and L5 points of the Pluto-Charon system are unstable. Charon cannot have stable Trojan objects.
Therefore, the Trojan test confirms it. Pluto and Charon are correctly a binary planet system. The physics just won't allow one to be a satellite of the other.
And now for our original question,
Oh.
what about the Earth and the Moon?
Well, Earth is about 80 times heavier than the Moon.
Which is more than 3 times the 25-to-1 cutoff.
So the Moon passes the Trojan test with flying colors.
It does. This confirms the Moon is definitively a satellite, a true moon, because the physics allows for stable Trojans to exist in this setup.
I love that it confirms our intuition there, but where this really shines for me is where the old tests failed so badly, in systems like Jupiter and the Sun.
Yes, this is probably the best validation of the Trojan test. Remember how Jupiter's barycenter with the Sun sometimes pulls outside the Sun's surface?
Yeah, and the old test would sometimes call it a binary pair, which is just wrong.
It's clearly wrong. The Trojan test fixes it by asking one simple physical question. Does the system have stable Trojans?
And with Jupiter, we know the answer is yes.
We know it does. Jupiter has huge swarms of Trojan asteroids orbiting ahead of and behind it. That physical fact proves that the mass of the Sun must be more than 25 times the mass of Jupiter.
And it is, by a lot.
By over 1,000 times, actually. So the Trojan test accurately classifies it as a star-planet pairing, no matter where the barycenter happens to be on a given Tuesday.
The power of this is just. It's undeniable. You're shifting the definition away from some random imaginary point in space and anchoring it to the actual stability of orbital mechanics. It's physically meaningful.
It is a true physical boundary. On one side of that 25-to-1 ratio, stable orbits are physically possible. On the other side, they're impossible. And that condition is the same whether you're talking about a tiny moon or a giant planet orbiting a distant star.
And the sources point out this has massive implications for classifying exoplanets.
Exactly. When astronomers find a new system, the Trojan test provides a robust universal criterion. It helps them decide, is that a true exoplanet, or is it a low-mass binary companion? The argument is that this should be the standard for any two orbiting objects in the entire universe.
So we've gone on quite a journey. We've moved from a messy, location-based definition to this clear, physics-based one founded on that 25-to-1 mass ratio for orbital stability.
It simplifies everything and gives us a much deeper understanding of what really makes a moon, and it leaves us with one last really fascinating detail about our own system.
Oh.
Because the Earth-Moon mass ratio of 80-to-1 passes the Trojan test so comfortably, it means the Moon can, in principle, have its own stable Trojan points.
Wait, so just like Jupiter has its Trojans relative to the Sun,
The Moon could have its own moon Trojans orbiting ahead and behind it relative to the Earth.
have we found any?
Well, the mechanics allow for it. We haven't definitively found any sustained natural ones yet. They'd probably be very small, very hard to spot, or maybe they've been kicked out over billions of years. But the stability window is physically there.
Wow.
So, the provocative thought we'll leave you with is this. If the Moon's Trojan points are physically stable, what would a tiny moon Trojan look like, and what would it actually take for us to go out and find it?